Hello, here we're starting the linear modeling worksheets. If you go to page 546 in your book, you can find the words to complete these sentences. When you plot data on a scatter diagram, remember scatter diagrams? They're found in Excel whenever you do your science fair and you have two different variables. You make scatter diagrams. The independent variable goes on the x-axis or horizontal axis, and then the dependent variable goes on the y or vertical axis. Every year at science fair we go back and remember that. Okay. Correlation means that there is a relationship between the two variables. So now we're going to draw examples of fake data distributions with certain types of correlation. For example, actually this should be positive correlation because I don't want to put negative correlation twice. Positive. Okay. Positive correlation looks like this, where you have data points going in an upward trend like something is growing. Negative correlation, on the other hand, looks kind of like this, where you have data kind of going in a downward direction. And let's see, next one is no correlation. No correlation just does not look like any kind of line. Linear correlation is anything that kind of looks like it's arranged in a line. It could be in any direction. Nonlinear correlation, maybe you're going to have like some kind of pattern or trend there, but maybe it looks like a parabola, for example, not linear. What about strong positive correlation as opposed to moderate positive correlation and weak positive correlation? Well, the strength of the correlation just means how tight the data is. So strong positive correlation would be in an upward direction because positive means upward, and the data would be very tight in the line. Weak, on the other hand, would look like it's basically a line, but maybe not too tight. So, like, the data is maybe floating around in a cloud around the line. And then moderate would be somewhere in between the two. Strong negative correlation would be tight in a line, but it would be a downward trend line because negative correlation means it's going down. Weak negative correlation would be a trend that's going down, but in a generally line-like shape, but maybe a little more like a cloud. Okay. Page 548. Outliers. Draw a data distribution which has an outlier in the grid to the right. Explain when an outlier should be kept and when it can be discarded. So let's say you have a pretty good distribution in your science fair and you have one data point which is not together with the rest. An outlier is this data point which is not together with the other data. Explain when an outlier should be kept and when it can be discarded. Well, what the book says is if you have an outlier, if it's a real piece of data that's not an error, then you keep it. What do we mean by an error? Well, like let's say you graphed it in the wrong place, or you recorded it wrong somehow. So in those cases, of course, you should discard it. But if it is a real piece of data, then you should not discard it. Okay? So basically, if real piece of data not measured or recorded wrong, then you keep it. Okay. Causation, the concept of causation. This is really important because sometimes on our internal assessments or in real life, we get sloppy with our vocabulary and we say something that makes it sound like one factor causes the other factor when in fact only the two factors are related or correlated with each other, not one being the cause of the other. So it says, give an example from your life of two quantities or variables that are correlated in which a change in one of the variables causes a change in the other variable. So let's say the temperature. The temperature causes less thickness of clothes. Okay? So here there's not only a correlation, but the temperature causes the thickness in the clothes to be less. And it's not the other way around, right? It's not thin clothes cause hot temperatures or vice versa, right? The temperature is the one that causes the clothes to be thinner. Now given a similar example, except for this time, give an example where the two variables are correlated, but one does not cause the other. Let's take thickness of clothes correlated to, but does not cause, hair length. Okay? So maybe there's a tendency for hair length to be shorter when clothes are thinner because both happen when the temperature is hot. So they're both caused by the temperature being hot. They're not causing each other, although they both happen at the same time. Okay, it's just a coincidence that both happen when the temperature is hot. One does not cause the other. Okay, so that's trying to explain the concept of causation, which is different than correlation. Okay. Page 2. For the following scatter diagrams, comment on the existence of any patterns, positive, negative, or no correlation, and the relationship strength, 0, weak, moderate, or strong. Whether the relationship is linear and whether there are any outliers. Okay, so let's look through these and first say positive, negative, or no correlation. So this one looks like no correlation. It doesn't look like a line that goes up or a line that goes down. This one I would say is positive. This one I would say is negative. One kind of goes up, one kind of goes down. This kind of goes up. This kind of goes down. This kind of goes up. Okay, next one it says the relationship strength, 0, weak, moderate, or strong. So if it's no, we don't need to classify the relationship strength. There is no relationship. The next one looks like, drop my pen. The next one looks like it's weak. The next one looks like maybe moderate. The next one looks kind of, I don't know, weak, I guess. We're not going to know for sure on these. We're kind of guessing. Moderate. Or strong. Might be strong. I'm going to write strong. Strong. And the next one maybe is moderate or weak. Last thing, whether the relationship is linear. Okay, so in the first one there's no correlation, so it's not linear. And in the others, I think we can put linear for probably all of these. Linear, 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 except for the first one. Whether there are any outliers. Okay, let's mark the outliers if there are any outliers. There's one, and that's pretty much it. Okay, so just 2 have outliers. All right. Number 3. 10 students participate in a typing contest where the students were given 1 minute to type as many words as possible. The table below shows how many words each student typed and how many errors they made. Draw a scatter diagram for the data and name the student who was best described as slow but accurate, fast but accurate, and outlier. Describe the direction and strength of correlation between these variables. Is the data linear? Okay, so we're gonna try to graph this data here. I don't think I can make it any bigger. There we go. Okay, so let's see. First, I'm going to divide the graph up into 0, 10, 20, 30, 40, 50, 50, 60, 70, 80, 90, 100. Okay, and then for the vertical axis, looks like my biggest numbers are about 30. So I could go 10, 20, 30. Okay, can we? Yeah, I think that's about the most we can divide it. Okay, and so let's start graphing some of these pairs. So 40, 11, for example. 40, 11, there's one. 53, 13. 53, 13. 20, 2. 20, 2. 65, 20. 65, 20. 35, 4. 35, 4. That's very low. 60, 22. 60, 22. 85, 30. 85, 30. So 30 is way up there. 30 is way up here. So 85, 30. And 49, 16. 49, 16. And 35, 27. 35, 27. And 76, 25. 76, 25. Okay. That's the scatter diagram. Let's see, who is slow but accurate? So let's mark what these are. This is number of words. And over here on the vertical axis, we have errors. So slow but accurate would be like this person right here, which is, looks like it's 20, something, like this person here. Then there's fast but inaccurate. So fast but inaccurate would be like this person here, which is 85, 30. And then an outlier. An outlier would be this person here, which is about 35, 27 or something. Okay. All right. Describe the direction and strength of correlation between these variables. I would say, is it positive or negative? Well, it's kind of in an upward trend, so it's positive. We could say it's linear. And we could say maybe it's moderate. Might even be strong, but okay. Is the data linear? Yes, we said linear. Yes. Okay. Looks kind of like a line. I'm going to draw a rough line through it so you can see which line I'm picturing there. All right? Okay. Last problem. Number 4. Scores awarded by 2 judges in an ice skating competition are shown in the table. Construct a scatter diagram for this data. Judge A score on the horizontal and Judge B score on the vertical. So I'm going to use this here. So there's Judge A and Judge B. Both of these are kind of on a scale of 1 to 10. So we'll put 0 to 10. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 10. Okay. Complete and complete the following comments. There appears to be blah, blah, blah. Okay. So first we need to graph all this data. So first 5, 6. 5, 6 is there. 6.57. 6.5 and 7. 1, 2, 3, 4, 5. Oh, it'll be here. Okay. Next one, 8 and 8.5. 8 and 8.5. Next one, 9 comma 9. That's right there. 4 comma 5. That's right there. 2.5 comma 4. 2.5 comma 4. Right there. 7 comma 7.5. 7 comma 7.5. Right there. 5 comma 5. Right there. And 6 comma 7. We're almost done. 6 comma 7. Right there. 3 comma 4.5. 3 comma 4.5. Right there. Okay. Well, it's pretty good. All right. Now, there appears to be blank correlation between Judge A's score and Judge B's score. This means that Judge A's scores increase, Judge B's scores also increase. So we could say the word they're looking for there is positive, right? Because positive correlation means that as the independent variable increases, the dependent variable also increases. So it's like an like a growing trend like that. So it is positive, and we could say it's linear. So it's a positive linear correlation. So that means that Judge A's scores increase, Judge B's scores also increase. Last of all, would it be reasonable to conclude that an increase in Judge A's scores causes an increase in Judge B's score? Not necessarily. I mean, maybe if you have like maybe an inexperienced Judge B and he looks over at Judge A's score before he writes his down, I can see then maybe Judge A's score would cause Judge B's scores to be higher or lower, but normally you wouldn't expect the judges' scores to influence each other, so no. Okay? And they're not exactly right, and it's normal for one skater to be judged about the same by both judges, right? Unless like one's from Russia and the other one's from America. Maybe then you wouldn't have that. Okay, so that's the end of page 1 and 2.